Hi and welcome to this our second short in sustainable engineering. Today we're going to look at the science of sustainable design and how this affects our environmental and carbon footprints. Within this presentation we'll quickly look at the following areas. We'll understanding the vernacular within our designs, why thermal properties and materials are important, how the location will affect the results, what in our structures can add to heat loads, and we'll give a basic insight to some tools for assessing our structures and software which can be used for thermal assessing different elements within the structure. Understanding the vernacular is an important area. As you can see in the history of our buildings, we have used more and more energy use over that time period. And this is not a new story. It's been around for thousands of years, from the days of hunters and gatherers all the way up to modern consumerism. As we have developed as nations and as industry has moved on, we've used more and more energy, and this has been specifically seen in the last 200 years since the Industrial Revolution. The use of coal and other carbon products has driven up cheap energy, driving our industries forward. But this has had a great impact on the world as we moved. As you can see in the chart, as we've moved up industrially, our impact on the environment has increased and increased. So how can we move away from this cheap energy which we use within our structures? Well, actually there's many different methodologies. On the right hand side of the screen you can see a chart looking at prevailing winds, which is a methodology that's been around for hundreds of years, which drives prevailing winds into our buildings, pushing out the stale internal warmer air out through high ventilation and cooling down the buildings. It uses such things as wind catchers which catch high cooler airflows and pushes them down into the building and then draws out the warmer air at higher levels on the leeward side of the building. So we need to understand what the thermal properties of materials and why they are important in our structures. No matter what building we build, it will have a thermal imprint. It could be that a earth building as shown on the far left hand side of the screen to a modern day grand designs as shown in the centre of the screen, or as our operational tentage, or even an old English country cottage as shown on the right hand side. All these buildings have to deal with the movement of heat or cooling throughout their structures. So it's important that we know how to deal with this. As you can see in the two diagrams of the screen, we are either resisting the movement of heat to the outer areas of our buildings, or we're trying to reduce the transfer of heat from the solar radiation on the outside towards the cooler inside of our buildings. And the way we manage this is how we keep control of our energy use. If we don't manage it effectively, we will use more and more energy in either heating or cooling our structures. Also, the location of where we work or where our buildings are placed greatly affects them. And we need to understand some of the basic things on how the location of our buildings will affect them. Be that building something in a temperate location in the UK, in a hot temperature such as Kenya, or as a cool temperature somewhere like the Arctic. Our buildings need to be able to deal with these. So can you have a standard design which works in all environments? Well, unfortunately, not very effectively. If you have a standard design which has to work across all climates, it will do so at a high energy demand. So when we're designing our buildings, we need to understand the weather conditions that they'll be put in. Be that the wind which is pushing on them, the amount of rainfall around them, if the any available natural screening around the buildings, and the temperatures which they're going to be subjected to. If you look at the diagram on the far right hand corner of the screen, you'll see that a number of different factors are being pushed against that building, and the building has been designed to maximise the use of each of them. As you can see that the sun in the middle of the summer is bearing down directly onto the top of the building. Well, it's been given larger eaves to prevent that sun rays shining direct into the windows, in turn reducing down the internal temperatures within the building, which is not directly heating it up through the glazing. Trees have been planted on one side of the building to allow the leaves and the great foliage to stop the sun rays penetrating into the building, giving that natural shading around the openings and the windows. But where in the lower areas of the tree where leaves don't normally grow, the prevailing winds have been able to drive underneath the trees, cooling down, and then drive through the opening windows on the south side of the building. They then drive through the structure to the high, smaller windows on the north side of the building, allowing the airflow to blow out. This is a great way of using different types of natural incidents to be able to reduce temperature in your building, reducing the effect of sun while increasing the use of wind. We also need to understand the location of different factors on our buildings. These two diagrams on the screen here show you how different weather conditions change across the planet. The one on the right hand side is looking at annual rainfall, and you can see that the yellow areas are some of the driest areas on the planet, where the purple areas and the blue areas are some of the wettest. And these can be side by side. If you look at Central Africa, you can see that the Sahara Desert to the north is one of the driest regions on the planet, while the Centre Delta across Central Africa is actually one of the wettest. So if you're looking at building a building in northern Egypt, that same structure is not going to be suitable for somewhere in South Sudan or Kenya, because the different falls in temperature and rainfall are going to be greatly different. The diagram on the left hand side actually shows the heat gains across the planet, going from dark blue being some of the coldest regions on the planet to red as some of the warmest regions on the planet. You can see that is a belt across northern Africa, Asia and the northern elements of South America. You'll get the heavy temperatures into drying up these regions. So some of the hottest regions are also some of the wettest ones, but also some of the colder regions are some of the driest ones. And we need to understand how these would affect our structures when we're designing them. So what other loads can affect our structures? Well, if you look at the diagram in the top right hand corner of the screen, you'll see that there's a number of things within a building which can add heat to the structure. The electric lighting, computers, the occupants themselves all add a dimension of heat to the building. Things such as our kettles in our workspaces, our fridges and freezers produce a lot of heat when they're in use. TVs, speakers, computers, monitors, people, animals, sunlight and natural lighting are all additions to heating within the building. The picture in the bottom right hand corner shows you that in the past we used to bring animals into our building to actually help heat them up. So in one area of the world these factors could be a great advantage to you, helping you heat up the buildings you're working with, where in another part of the world they could be actually a great disadvantage because you have to provide a cooling load to deal with them. So what tools are out there to help you understand what the heating and cooling loads within a building are and how well your buildings are performing to deal with them? Well, in the UK we use the Standard Assessment Procedure, SAP, which looks at a number of areas such as material use, thermal insulation, leakage of air within the building, how well we control our heating systems, how well we deal with thermal gains through openings, our fuel use and the use of renewable energies. But there's a number of other different systems out there. The BRE, use the British Research Establishment's Environmental Assessment Method, or the military have an equivalent called DREAM. But you'll find other ones across the world, such as the Leadership in Energy and Environmental Design, which is mainly used in the US. But there's a number of free tools out there that can also help you. The STBA's Retrofit Wheel, which we'll look at more in a second, is a great tool of just doing initial planning of how you would retrofit an existing building and what impact your works will have on it. And the US government have provided a free piece of software called Therm2, which you can use to assess thermal breaches within your building and then use them to be able to redesign the building to reduce them. So let's have a look at the STBA's Retrofit Wheel. This is a free piece of software you can use online, and when you go onto this wheel you just click on the different areas of the building you're looking to address. When you can click on them, you'll click on high to low amount of impact you're going to have on the building, and it will give you a brief description, as you can see in the center of the screen, of what that work will entail. Once you've completed all the different areas you're looking to address on the building, it will then highlight to you a number of technical and energy concerns within the building. Once you've completed it, it will produce a report, as shown on the right hand side of the screen, highlighting all the different areas within the building where it might be a technical or concern or might have a direct impact on the energy use within that structure. It's a great way of assessing a building when you're looking to refurb it or move it to a different type of use and see how your works will impact the energy use and the technical ability to resist external environmental elements within the building. I also mentioned the US software Therm2. This is a great 2D piece of software where you can import a CAD drawing element into it to assess it for its thermodynamics. In the center of the screen you can see an example. This is a traditional solid block wall opening above a traditional window. The concrete lintel above the window is providing good thermal properties, but above that in the top diagram you can see there's a large thermal breach in the brickwork above the lintel. Using the software, we've been able to add a 25mm insulation to the inside with a 15mm plasterboard placed over the top of it. This simple retrofit on the inside of the building has greatly reduced the condensation risk within the internal fabric of the building, reducing the energy release in there and warming up the internal environment. When you do a comparison that with a U-value and dew point analysis as seen on the right hand side, you can see that these simple additions has greatly reduced the U-value within the structure. You do need to take into account that greater insulation you put, closer the dew point will get, but this is a discussion for another day. But you don't need some online software to be able to do an analysis of a building. A simple Excel spreadsheet will help you be able to look at the different management strategies you can use in a building when you're moving them from one location to the other. This chart on the screen is a simple assessment of an office space which was designed and built in the UK, which is in an example A1. And it's been moved to Khartoum in Sudan and it's been assessed for different times of the year. The first slide at the table shows you the different temperature changes between the external and internal fabric. We then looked at the energy losses through that building fabric against them temperatures. We're then using an assessment of the air changes and how much energy would be lost against Tipsy guides. You can see how many air changes you would need to reduce the temperature to understand the energy losses within the building. Then looking at the metabolic gains, which we talked about earlier, of people, equipment, kettles, sunlight and natural light, and how these can affect the inside of the workings of the building. And how can you use them to understand the management strategy you need to implement in the building to reduce it. So at night, can you turn off a number of pieces of equipment to reduce the heat load they're producing? Can you reduce the amount of people required in the building to reduce the heat load created, reducing the amount of cooling you need? A simple assessment like this can enable you to manage a building for different times of the year and in different locations in the world to be able to reduce its energy impact. So that was a quick insight into looking at sustainable design. An area we would like you to discuss in your teams on your next project is how you can use softwares to understand the energy outputs of your building in the design. I hope you've enjoyed this presentation and look forward to speaking to you on the next one.